Okay. Our very last actual lecture. And let's begin. So today is our very last actual lecture, which is going to have material, which is going to be on the test. And then on Friday, we are going to have a review session. So please bring questions and I'm going to solve any questions you want me to solve from the textbook. Now, today's discussion is going to have tons of questions on it. I actually pulled many of them from kind of previous discussions, maybe change some numbers someplace. But the fact is, it doesn't mean the questions which are going to be on the discussion are going to be on the test and vice versa. We have covered lots and lots of material. So the best way to practice for the final is probably do the last homework I am assigned and then try to redo all the discussions. Try to do problems from the textbook, like literally pick a question from, like, I don't know, each chapter which you feel like those are type of questions we covered, and try to solve it. So the test is cumulative. However, it's going to probably have a bit more heavier questions or more questions on topics we covered since the last test. Okay. So today's discussion is like really long, and it's not collected in any way. Those are just questions to remind you what type of questions we had. However, there are more questions we covered, so literally it's not everything. Yep. Okay, on that note, let's move on and let's kind of remember where we were. So we have been studying chapter 10, and chapter 10 has been talking about graphs. So originally we talked about sets, correct, and operations you can do on sets. And then the graphs are defined to be a combination of two sets, the set V of vertices and set E of edges, which are connecting those vertices. We did talk that you can do unions of graphs, correct? And kind of like an intersection to some extent, or you can take a graph and like make it smaller by taking a subset of these, so creating subgraphs out of it. We did talk about things like graphs can be directed and undirected. They can be simple. We talked about degrees of the graphs and a couple of important theorems. I did post a quiz. Now, this quiz is kind of a bit of a cheating because it has more questions. The questions are kind of on a graph theory, which was not about your last homework. However, since we collected last homework, I kind of feel like you probably did the relations and you had discussion on relations and you didn't cover graphs that much. So the quiz you have out there is about graph theory. Okay, so what we also did is we discussed that in a graph, you can have a path and you can have circuits. And then we talked about two special circuits / paths, which are Hamiltonian and Euler paths. Now, one more important topic we covered was about, I call it similarity of a graphs, and the official word for it is isomorphism, correct? So we talked about that two graphs can look very different, but still be isomorphic to each other. So, and we have discussed how to find the isomorphism if you feel like two graphs are the same. We talked about bipartite graphs. So literally we had lots and lots and lots of topics just in chapter of a graph theories. Now, what do you think is how graph is connected to relations? Because the thing we had before graph theory was the relation, correct? So we have a connection between graphs and sets, correct? Because graph is collection of two sets. Is there, do you feel like, is there any connection between relations and graphs? Yes, no, maybe? You should know the answer, at least one way. Okay, yes is good. So do you remember when we talked about relations, we said always represent relation using graph, correct? Remember, we represented relations using graphs. So there is a connection between relations and graphs. And then we also talked that graphs can have some property like connectivity. So what we're going to do today is we're going to continue kind of talk about graphs. And we're going to talk about two special problems and like a case. So let me start by sharing the screen. And I'm going to introduce to you a new type of graph. And again, it's going to be cheating because I'm not drawing that disaster. So what I have here, as you can easily see, is a graph, correct? Now, partial matrices are not type of the graphs. Matrices can be used to represent graphs. Yes, so you can take a matrix and you can draw graph from it, and you can take graph and you can represent it as a matrix. So it's back and forward type of thing. However, it's not really a graph. Okay, you can think about it as a representation of a graph, but it can represent different things other than graphs. And in matrices, you do not have vertices and you do not have edges. Matrix is just a different data structures. Okay. So let's look at this graph out here. This graph kind of looks similar to what we've done with a tiny difference. So it looks similar because we have vertices, correct? In this case, the vertices are representing different cities. And we have San Francisco, Los Angeles, Denver, Chicago, Boston, New York, Atlanta, and Miami. We also have edges that connect our cities. And you can think about it as those edges actually represent flights. Okay. So when you take a flight and you fly from San Francisco directly to New York, the amount of mileage you're going to pass is going to be 2,534, for example. And then in order to fly from San Francisco to Chicago, the number of miles you fly is going to be 1,855. Now, you can also generate something similar by using flight times versus mileages, correct? The graph below is very similar, but represents a totally different data. What it introduces to us is a new concept. The graph can be weighted. So a weighted graph, oops, is a graph G together with W for each edge in E. W of E is weight of E. So pretty much we kind of have like a function. So back to my picture out, here's the graph I showed you is a weighted graph, and you can see weights are in blue. So every edge has kind of function associated with it. Now in the first top graph, my weights are mileages, correct? In my second graph, my weight can be a time, yes? So now let me introduce to you a new interesting problem. So the interesting problem is, what is the shortest path between two vertices? So I can do, what is the best way for me, the shortest path for me to get from San Francisco, for example, to Miami? So now, weighted path problem can be defined differently. Sometimes I can say, if I have a traditional graph and there are no weights on it, I can say what is the shortest path from point A to point B on a graph. And this is shortest for me is going to be number of edges I'm going to get. So I'm going to say each edge is 1, correct? However, if I have a weighted graph, my shortest path is supposed to be either the least time, yes, or it has to be the least weight, pretty much. So I'm combining the weights. So let's look at mileage, and we're going to travel from San Francisco to Miami. Okay, so I'm traveling from San Francisco to Miami. How many different passes do you see there? 1, 2, many? I think many is going to be a good idea, yes, because I can go from, I don't know, even from San Francisco to New York, and then from New York to Boston, and from Boston to Chicago, and from Chicago to Denver, and from Denver to LA. Well, actually, no. You know what? No, let's go back. Let's not go to Denver. From Chicago, we will go to Atlanta, and from Atlanta to Miami. Here we go. I have a pass. I did not repeat any cities. Lovely, right? So you can understand, but my shortest path never should have circles, correct? Because if I circled, I added some extra things. So what we need is we need to look at different type of passes and figure out which one is going to be the best as far as we travel the least amount of miles. So one way of doing things is going to be to travel from San Francisco to New York, which is 2534. And then from New York to Miami, this is going to be 3624, 3624. So let me write it down because otherwise I'm going to forget. 3624, correct? Which is 2534 plus 1090, I believe. Yes, 3624. Yes. Let's try another way. What if we go from San Francisco to Chicago and then to Atlanta and then to Miami? So let me actually make my graph a bit bigger and scroll tiny bit. No. Here we go. Okay, so we are going to have 1855 plus where am I? 606 plus 595. Okay, who already did our beautiful math? Let me grab my calculator. I'm not greatest at counting today. 1855 plus 606 plus 595. Oops, what have I done? Okay, this one is 3056. Looks better to me. Now somebody, Raven, is suggesting San Francisco, Denver, LA. Wait. What is the suggestion? San Francisco, Denver. No. Okay. Can we see anything else which is promising? I think this one might be the shortest one. It kind of looks like it is. The reason for it is I can see that going from San Francisco to Chicago, for example. Well, 7, yeah. Yeah, I think this is going to be the best shortest pass. Not short, well, shortest as far as least mileage pass from me. And again, you can check it by trying all possible combinations and so on. Yes. So do you understand the idea of the question? You probably would agree that it makes sense that this problem is kind of very realistic problem and can be used in tons of different ways, right? And the fact is, what I just said as far as let's try all possible tests and all possible passes and calculate the weight for it. This is probably not the best one. Agreed? Like we probably want to do a bit better than that. There are lots and lots of passes, and some of them kind of don't make sense to even try, correct? So what we're going to talk about today is we're going to try and talk about an algorithm which is called Dijkstra algorithm. So we will be doing Dijkstra algorithm. For finding shortest path in weighted connected simple graph. All weights must be positive. Now, the idea for all weights must be positive has come from the fact that if I have a negative weighted path and I have a circle, I can continue circling, 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 and my weight is going to become smaller and smaller and smaller and smaller. So I'm going to get infinity, correct? So we really must have all weights in a positive way. So one way to do it, what if you do have negative numbers? One way to do it is take the minimum of weights, if it's negative, and add the same positive amount to all the nodes by raising all of the numbers, and then you're going to get your positive things. So you can still do it and not allow those negative loops. However, algorithm, the way it is written is going to be broken if there is negative ones because of those negative loops. So let's look at the algorithm. And again, I'm going to be cheating, and we're going to take the algorithm directly from the textbook. Okay. So what we want. We have a graph, weighted graph. The graph is going to have vertices with 0 through the n. We're going to start with vertex A, and we're going to find the shortest path to Z. So we have A as starting point and Z as a terminal point. And we also have length W, which is the weight pretty much, yes, from Vi to Vj. For every edge we have out there, we have a weight. Now, we might have W of Vi and Vj to be infinity if we do not have some edge in G. So we kind of can assume all edges are out there. It's just, it's infinity if we do not have the edge. That makes sense? Because we do not want to take it. Infinity is already bad. We probably can do better, correct? So we kind of want to ignore it. So what we're going to do is we're going to go from I equal 1 to n. So this is number of vertices I get. And we are going to set L of Vi to be infinity. So we are going to kind of put infinity on every single node. Yes, so I have now L, which is a special function list for every single node in it infinity. Now, what we are going to do is we're going to start the algorithm. We are going to go to the node A, and we are going to put 0 as an L of A. This is our starting point. The weight of it is 0. I didn't travel anywhere. Now we're going to create an S, and at the beginning, S has nothing in it. So while Z, this is our node, does not belong to S, we are going to take U, a vertex which is not an S, with LU minimum, and we are going to add to the S the U. And then for all vertices V, which are not an S, we are going to check if the weight of L of U plus VUW is less than LV, then we are going to change L of V to be L of U plus WUV. Pretty much this adds a vertex to S with minimal label and updates the label of the vertex not an S. So we're kind of trying to find the weight of each of it, of how quickly I can get to this node pretty much. And then we're going to do it until we calculate LZ. LZ is the length of the shortest path from A to Z. So now we want to look at the example. So we are going to grab a 4-point A. Where is my picture? So let's do an example. I know the algorithm looks complicated, but actually it's pretty easy to execute as soon as you are going to understand how the algorithm works. So we have to start with the traditional graph. Here we go. And I can think about it, this graph represents some type of network, for example, and I want to know what is the best speed I can get if I need to send my, I don't know, message from one of the vertices to another. There are tons of computer science, real life examples when you need the shortest path algorithms. So we have our nodes A, B, D, Z, E, and C. And we have weight, which is 2, 4, 1, 5, 8, 10, 2, 6, and 3. Now, L is going to be red in my case. L of V is going to be in the red. So I'm starting by putting infinity everywhere. And I'm trying to find A to Z shortest path. In this case, this is what we're trying to do using Dijkstra. And this is his family name. So it's, you know, like the person who developed the algorithm. So we have infinity everywhere and we have 0 out here. Okay. So what I do now is I'm going to check neighbors of A. So I'm starting with smallest one out here. And what I need to do is I need to find the L if I can. So if I have L lengths, if I have a path, not a path, if I have edge from A to B, what I'm going to do is I'm going to replace the B value to be 4 because the weight of this edge is 4. I have another edge from A to C, and this one is going to be 2. Okay? I can even in here remember how I got this number. So in here, I know to get 4, I used A, B. And then here to get this one, I used A, C. Correct? So pretty much next, what I need to do is for nodes B and C, yes, I will take the minimum one, which is going to be the 2, and I'm going to do the same thing from there. Now, one thing to remember, I do have an edge from C to A, so I can make the weight of A to be 2. Do I want to make it 2? Do I want this number to be as small as possible or as large as possible? Small, correct? So it's always peak minimum value you can get, correct? So by doing that, what I will be able to do is I will be able to change value of 4 now is going to become 3, correct? And how do I get there? Where I get there using A, C, B. How did I got it? Well, I looked at this node out here. It is connected to B using weight 1. So you do 2 plus 1, which is 3, and you check, is 3 better than what I have written so far? And I was having 4. So 4 was bad. So I have to change it to be 3. Does that make sense? Whom else should I update? So you're always looking at the one smallest. We are going with the C because C has smaller values than B, and we are already done with A. So you pretty much can think right now that my S has C, B in it, but I focus on C because C has minimal weight. So now what C is connected to is it's connected to E, correct? So we can change this infinity to be what? So I can get from C to E. Okay, so 10 is the most common mistake. We are going to do L of V plus weight of edge from V to U. So we have 2 plus weight, which is 12. Don't forget, I'm always interested at pass from A. So this is why we add. So this one is going to be 12. And the way I got here is A, C, E, correct? There is one more H directly from C, which is C to D. So I can definitely change this one to be, so I'm coming from C. 10 it is, and the way we got here is A, C, E. Okay? Now, I am done with that node C. I already explored it. So in my set S, I have nodes I did not explore yet, but I already touched them. So it's not infinity. So I have kind of, I can pick one of the B, D, or E. So which one am I picking? Which one has the smallest value? B, correct? So now we're going to do the B. So when we do the B, we need to look. From B, we can get to D. And the weight in this case is going to be, is 8 better than 10? So we're going to fix it. We're going to say it's 8. So we are actually taking the path A, B, D to get here. We can get from B to C, but we are not worried about it because we already did the C and we did the A, so those are not going to be bigger, correct? They're only going to be smaller. So can I get from B using one edge to any place else besides the D? Can I get from B to anything besides D using one edge? Something we didn't cover yet, something we didn't do yet. Now think about it. If you can kind of in head, you can do it. You're going to do B to C is 1. 3 plus 1 is 4. 4, is it better than 2 or not? No, so it's kind of useless to do it backwards. It's never going to go well if you go backwards. So you ignore, if A and C already done, you do not go back to A and C anymore. The nodes you already totally explore, you do not come back to them. So finally, let's pick our next node. So the nodes we can pick from are the ones we didn't explore yet. So I kind of can cover the one we explore so that you know are those, correct? Those are the ones we explore. So now I need to pick up the smallest from what I got. So do I pick D or E? D, correct? So from D to get to E, I'm going to get D to E. What am I getting? D to E. 10 is correct. So this is bad. So the way we get here is A, B, D, E, correct? Now, I also can get from D to Z, correct? So from D to Z, this is going to be 8 plus 6, which is going to be 14, correct? I am still not done because I still have nodes to explore. So this is A, B, D, Z. Do I need to explore anything from D? No, D is done. We did the edges from D. Yes. And now who I have to explore? Who is going to be my next explorer? E, correct? Can I get from E to Z? Yes. What is going to be the number? Aha, 13. So what is my shortest path? Has weight 13 and is, what do we do? A, B, D, E, Z it is. Okay, let's see. 4 and 5, 9. Wait. A, C, B. Yes, where did I lose the C? A, C. Sorry, I'm missing C everywhere apparently. Yes. So A, C, B, so 3, 5, 2, yes, 3. So my pass is 2, 1, 5, 2, 3. So how long does it take? Well, I actually explore every edge, correct? Pretty much. So the running time of this algorithm is generally n square. So I feel like you probably want another Dijkstra example. So the Dijkstra is very special type of algorithm. It's called greedy algorithm. And the reason for it is because I always greedily pick the one with the smallest pass. Okay. So I'm going to do quickly another example for you. And you're going to help me out, but we are going to go pretty quick because I still want to talk to you about trees. And we only have like 9 minutes left. Okay, 1, 0, 1, 2, 3, 4, 5, 6, 7, 4, 8, 7, 9, 14, 10, 2, 7, 6, 2, 1, 8. So I'm going to mark those ones in circles so that we do not confuse, sorry, so that we do not confuse our vertices with weights. And I'm going to use my length. So you can pick any 2 nodes you want, but let's travel from, I don't know, 0 to 4. This is the shortest path I want. So I'm going to start with the node 0. I'm going to put its things to 0. I'm not even going to put infinity. I'm going to remember it in my mind, okay? So now I'm going to start. So 0 is connected to 1, and 0 is connected to 7. So I change their weights. So I did this node. The next node is I need to pick between 4 and 8. 1 I didn't visit yet. So should I pick 1 or 7? 1 is the one I pick because it has the least thing. Good. Keep going. Now I'm trying to see where can I get from 1. Well, the only node I can get from 1 is to 2. So I need to change 2L to be how much? 12 is correct. So now I need to pick either 7 or 2. Which one do I pick, 7 or 2? Which should I visit next? 7. Where can I get from 7 to? From 7, I can get to, nodes 8 and 6, correct? 8 and 6. So I need to change this one is going to be 15, and this one is going to be, the 6 is going to be 9 is correct because it's 1 plus 8. So which one do I pick next? Who are my options? My options are 2, 8, and 6. Which one do we grab? 9. Okay, so we grab node 6 with the weight 9, and we're trying to get to other nodes. What nodes can I get to from the node 6? I can get to node 8, and the weight is going to be 6 plus 9, which is 15. Is 15 better than 15? No, so let's leave it the way it is, correct? So I also can go from 6 to 5. And what is going to be my weight here? 11 is correct. So 12, 15, or 11? 11 is the peak, so node 5 is the one we visit next. So who can I get to from the 11? From the 11, I can get to node 3. So my thing here is going to be 25. I can also get from node 5 to the 4. So my value here is going to be 21. Do you agree? Okay. The most common mistake is to say now I'm done. There are still things I need to check because maybe I can do something better. Now imagine if I'll have just one line, if I'll add a line over here from 2 to 4 and give it the weight of 1, yes, it's going to be 13, which is going to be much better than 21, correct? So I have to keep on going for every node until everything is kind of yellow, okay, everything I can achieve. So now who do I pick next? Node 2 or node 3? 12 or 25? 2. So from 2, I can get 12 plus 7, which is 19 to get to here, correct? So I can fix it to be 19, correct? I also can get from 12 to here, and I can get 14 here, right? So who do I pick next, 14 or 19? I need to pick 14, but guess what? He only connects to the things which are yellow, so I do not need to recalculate. It's going to be worse no matter what. Okay? Because you always pick the best one already. So you can kind of double check, but 14 plus 6 is 20, definitely 9 is better, correct? And 14 plus 2 is 16, 12 is definitely better. So, you know, don't do it. Finally, we need to check this one. So 19 plus 9 is 28, and 28 is not good. So the next one is this one, but we just report whether shortest path weight is 21. Now, this time I did a lousy job. I did not remember exactly what path I took, correct? But I can mark it for you. So what we really took is 8 plus 1 plus 2 plus 10. This is the path. So generally, you can write down what path you're taking if you want to remember it. So this is how Dijkstra works, and he does remember the actual path. I do promise you to have a question about it on a test. So I'm going to post your homework assignment of everything we did. We kind of have just one. We have 1 minute, but I still want to say something. So the chapter we didn't cover, and I kind of wanted to at least touch base on it, is chapter 11, and it talks about trees. So what I want you to know before going to any next class, that trees are special graphs. They do not have circles at all. They have root, and we draw them like that. So I cannot go back ever. So the very top one is called root. Everybody you're connected to on a level below are children and parent. So there is a children-parent relation. So this is on top. So if we call it A and B, B is parent of A and A is child of B. You do not need to know it for the test, but you will need it in algorithm analysis, and hopefully it's going to be covered from the very beginning, but I want you to be familiar with the term tree because it's an important term and you're going to see it in computer science a lot. We actually have special binary trees, which are very, very important for computer science. So anyway, that's all I wanted to cover. We're going to have a review section on Friday, and I'll see you all on Friday, and send the test as a Friday after. Have a good day.